happens. Okay. Don't worry, because I'm doing the same lecture tonight, so I'll just post the since I now have a YouTube channel, I'll post that one. Hopefully, I won't forget to start recording that one, and if necessary, I'll just do an extra recording of the first examples so that you can see them. So, by the way, don't forget to go to our YouTube channel. So it's a very exciting channel with a lot of math videos that are probably not as good as Khan Academy. Yes, that would be really interesting. Okay, so find and classify all local extrema of x to the fourth. So of f of x equals x to the fourth. So this is something that probably looks like it's going to be very, very simple. You have f prime of x equals 4x cubed, and f double prime of x equals 12x squared. So what we know is that in order to find, what we want to do is find the critical numbers. So 4x cubed, so that's the first derivative, equals 0. That implies that x equals 0. So 0 is a critical number. All right, so now let's use the second derivative test. What we do is we plug in the critical number into the second derivative so we can see whether this is sitting atop a concave down function or at the bottom of a concave up function. So let's see what happens. Take f prime prime of 0, giving us 12 times 0 squared equals 0. And so 12 times 0 squared equals 0. And if you notice that means the test is inconclusive. Now what's going on here? Draw the graph of y equals x to the fourth. Looks a little bit like a quadratic, but not every u-shaped function is actually a quadratic. There are a lot of different u-shaped functions in math that are not, it's not a parabola. A lot of different u-shaped functions in math are not parabolas. It's really only quadratics that are. So what's going on here is this function flattens out so much at the bottom. I've drawn the flatness in kind of an exaggerated way that it doesn't really have any concavity at 0. It's still concave up here, and it's still concave up here. So this is not an inflection point, even though f double prime is 0, because concavity doesn't change across the point. And in fact, it certainly looks like this is a minimum value. So the only thing you can do is go back to first derivative test. Okay, so all right, so the first derivative test tells us that we pick points on either side of the critical number and we test them. So what we can see is we plug in f prime of -1. That's going to be 4 times -1 cubed equals -4, and f prime of 1 equals 4 times 1 cubed, which equals 4. So here we have negative and here we have positive. So we know by the first derivative test, if it's to the left, if it's negative to the left of if it is negative to the left of the critical number and positive to the right, then that means, of course, that the function is descending as you get to the critical number, ascending, and that indicates that x equals 0 is a min. So this is a case where clearly we do have a local minimum value, but we can't detect it through the second derivative test, and that's sort of the hazard of the second derivative test. It's easier to use, but only when it works. The first derivative test is always conclusive. The second derivative test is sometimes not conclusive. Okay. All right, so now let me get back to let me just get back, let me get to the next topic. What you're talking about is graph sketching. This is going on to section 4.6. Okay, so the what we've seen is that based on what the derivative of a particular function is, it at in an interval, the function has a certain appearance to it. And what we've been doing is taking functions that are known and describing their appearance, really. We're saying this is increasing, it is decreasing, it is concave up, it is concave down. We can do this process in reverse by taking functions where we don't really know what they look like, but we find their derivatives, and from that we can draw the function using using these facts about what they look like. So just the four that we've learned in this chapter are, we've learned that increasing functions look like this, and decreasing functions look like this, and concave up functions look like this, and concave down functions look like this. So this gives you some idea of if you know that the derivative, let's say the first derivative is negative and the second derivative is positive, it gives you some idea of what the shape of the function is. You may not be able to get a very accurate drawing, but at least you can get a picture of it. And this is one of the exercises that just every Calc 1 student goes through, is trying to draw the function based on what the derivatives are. I have to say that this is, although this topic is very mathematically satisfying because it kind of brings together everything we've learned about derivatives, it's a little bit dull to demonstrate, which is unfortunate. This is one of the problems with teaching Calc 1 in the fall, actually. The particular cycle we have for review requires that some more senior professor come and observe one of my classes in the fall semester, and it's always in early November, which is always when we're getting to this exact topic. So I think the last 4 years that I've taught Calc 1 when I didn't have Calc 1 in the fall this year, but in the previous 4 years that I did, someone always came and observed the graph sketching lecture, and I was like, somebody's going to watch the most boring lecture of the whole year. But fortunately, what I've done is I've learned how to make it a little bit less boring by doing fewer examples but more in depth. So hopefully that works out with this. So let's see. Next topic of graph sketching. As we've seen, increasing and concave, the increasing and decreasingness of a function, the monotonicity of a function, and its concavity are not in any way exclusive of each other. You can have both, and in fact, there are different shapes. So here, this is what an increasing and concave up function looks like. It's clearly increasing because it's going that way, but it's also concave up. I don't know if it's surprising to learn that a function can be increasing but concave down like that. So this function is increasing and concave down. Here we have decreasing and concave up. And here we have decreasing and concave down. What you can see kind of is that if I point at the top one, concave, increasing and concave up, what we have really is a function that's not only increasing, but the rate at which it's increasing is going up. We have sort of a shallow derivative right there and a steeper one there. On the other hand, here we have a function that's still increasing. The actual numerical value of the function is increasing, but it's very steep there and it's kind of shallowing out like that. In fact, that's really, kind of the topic that that I thought was sort of timely here. This is where we get to what you've heard about in the news about bending the curve. So here we actually have, I've left the L out intentionally. This is a number of infections um, versus time. So if you think of this as sort of like March 1st, and maybe this is like March 30th or something like that. What you can see is this is precisely what we're talking about in the news, is that we're trying to do is we're trying to hit this inflection point where here we clearly have a curve that's concave up, and we're trying to turn it into one that's concave down. Obviously, we'd like to see that happen, but before that can happen, the first thing that we have to do is, where these red lines represent the rate at which infections are increasing every day, is we're trying to at least turn it to a point where the number of infections per day, even if it is increasing, is getting to be smaller and smaller and smaller, as indicated by these shallower red lines. So, well, I certainly don't claim that calculus has all the answers for the predicament we now find ourselves in. At the very least, you can now look at the curves in that they show in the news and understand what it is that they're talking about. So it's a big step for me not to claim that calculus has an answer to everything, because I usually think that a calculus does have an answer to everything. So okay, so one definition that we need in graph sketching is something called a transition point. So a transition point is either a local extremum or an inflection point. In other words, this is a point where the shape of the graph is changing, and that's really what I've written here. Is we're talking about some place where we have to consider that the graph is changing in some way. It's changing, for example, from being increasing like that to being increasing like that. So here, that's an inflection point. Or maybe it's changing from increasing to decreasing. So that's increasing, that's decreasing. Here, that's concave up, and here, that's concave down. So what we're looking for is we're sort of lumping all the different types of changes of appearance together and just calling them transition points. So essentially, what we're going to do is find all the transition points in the graph and then decide really which of these four shapes the graph has. The final piece of the puzzle that we need is also that, in addition to knowing shapes of graphs, we also learned about something way back in chapter 2. We learned about asymptotes, and we learned that y equals a is a horizontal asymptote if the limit as x approaches infinity of f of x equals a, or the limit as x approaches negative infinity of f of x equals a. And we learned that x equals b is a vertical asymptote if either the limit as x approaches b from the positive side of f of x equals infinity, or, and then there were four other combinations of that. I don't want to spend time writing them out, but I could have b approaching from the negative side, and I could have the limit equal to negative infinity. So we had all those different combinations. So based on the four things we now know in this diagram about what the combination of increasing and concavity looks like, and also what we learned about asymptotes in chapter 2, we ought to be able to get a pretty good idea of what the graph of an arbitrary function looks like. So let me put up the process of how to sketch the graph of a function. So the first thing you do is you want to find the first and second derivatives. Sometimes I'll just give them to you in the problem. It's actually kind of a mess if you go and find them wrong and then use them correctly, because it's really hard to grade the problem then. So often I'll just give you the first and second derivatives unless they're really easy to find. Then what you want to do is find the critical numbers and the places where f double prime is either 0 or undefined. there's a certain lack of symmetry to those terms. I will say that the textbook we use in Math 135, which is the other Calc 1 course that Rutgers offers, refers to these as first order critical numbers and second order critical numbers, depending on whether you find them through the first or second derivative. Our book doesn't use that term, or at least I haven't seen it in the book. So I won't push that term on you, but basically we're just looking for places where the first and second derivative are either 0 or undefined. So next thing you want to do is determine whether the points you found in step number 2 are local maxes and mins. You can determine that either using the first or second derivative test. If you happen to have a non-zero concavity at one of those points, then if let's say that at this point f prime prime is less than 0, then I know that it looks like that, which means I also know that the first derivative must be positive to the left and negative to the right. If you get an inconclusive second derivative test, you have to go back to the first derivative test. And then, of course, for inflection points, the only thing you can really do is check whether the sign changes across the point. The sign of the second derivative changes across the point. And number 4, you just want to draw the arcs of the appropriate shapes. So if I know, for example, that this is, I'm writing this for monotonicity and concavity. So if I know, for example, that the monotonicity is increasing and the concavity is decreasing, and that here the monotonicity is increasing and the concavity is not increasing, sorry, is concave up, I meant instead, then what I know is that this point must look like that. In other words, it's increasing and concave down to the left, increasing and concave up to the right. So you can put in those little shapes and basically get what the shape of the graph looks like from that. So, okay. So let's sketch the graph of an exotic polynomial function. Exotic is not that's not some sort of term of art. I'm just saying this is a not very everyday kind of polynomial function. So second. Again. Okay. So I'll tell you, these types of problems take a lot of space. So when you do these on your own, just get a notebook out and plan to use a lot of paper for them. So that's why I've given myself some extra workspace. We'll actually draw the graph on the page that I indicated. But first, we're going to do is find first and second derivatives since they're not given. So the function f of x is 3x to the fourth minus 8x cubed plus 6x plus 1. So f prime of x equals 12x cubed minus 24x squared. Sorry, this should have been a squared plus 12x. And that is equal to, factor out the x, I get 12x x squared minus 24x plus 12, oh, sorry, minus 2x plus 1, which factors a little bit more, fortunately. Factors like that. So, and now f double prime of x, it's going to be easier to focus on this form of it in order to find the derivative. So that's going to be, sorry, not 24, 36x squared minus 48x plus 12, which equals 12, 3x minus 4, sorry, 3x squared minus 4x plus 1, which factors as 12, 3x minus 1 x minus 1. Okay, so we now have the first and second derivatives. So the 2 is I want to find transition points. So the transition points are going to be places where either the first or second derivative is 0 or not defined. Clearly, since the first and second derivative are just polynomial functions, they're defined everywhere. So I don't have any undefined points for the first and second derivative. I just want to find where f prime of x equals 0, and that's going to imply that x equals 0 or 1. So those are the critical numbers. And f prime prime of x equals 0 implies that x equals either 1/3 or 1. So one of these numbers actually appears twice. We have 3 transition points. So the transition points are 0, 1/3, and 1. Okay. Any questions so far? Okay. So what we want to do is try now. I'm going to switch to the next page just so I have more space. So 3, let's classify critical numbers 0 and 1 as mins or maxes, or neither. So we know that f prime prime of x, I'm going to use the second derivative test at first because it's kind of easier. So f prime prime of x was equal to 12 times 3x minus 1 times x minus 1. So f prime prime of 0 is going to be 12 negative 1 negative 1, which is 12. And f prime prime of 1 is going to equal 12 times 2 times 0, which is 0. So okay. So the all right, so the second derivative test was conclusive as to x equals 0. We can say that x equals 0, since concavity is positive, we can say is a local min. X equals 1 is inconclusive by the second derivative test. So we need to go to the first derivative test for that. So what we want to do is okay. So 0 and 1. We also had 1/3 as a transition point. What we want to do is we're going to use, I'm going to use 1/2 and 2 as the 2 test points on either side. So do the first derivative test for x equals 1. Call the f prime of x, let's see what that was 12x x minus 1 squared. So f prime of 1/2 equal to 12 times 1/2 times 1/2 minus 1 is -1/2 squared. So that's going to equal 12/8 or 3/2. And f prime of 2 equals 12 times 2 times 2 minus 1 is 1 squared. So that's going to be 24. So we can see that it's positive on both sides. We can see that it's positive on both sides of the critical number, the critical number 1. It's increasing here and it's increasing here. So that gives us that x equals 1 is neither max nor min. Okay, now what we need to do is we need to consider concavity at we need to consider the concavity at on either side of these points to see which ones are inflection points. So the two, where was it? The 2 points with the check marks, those were the ones where f double prime was found to be 0. So what we want to do is check the second derivative on either side of those points. We already have some places where we can do that. So what we're going to do is we're going to check, we're going to use these test values, that one, and that one. And that will tell us whether concavity is changing on either side of the 2 points with the check marks, 1/3 and 1. Just recall, the reason we're looking at those points is because these are the ones where f double prime was 0, so that's where concavity might potentially change. So f prime prime of 0 equal to, we already calculated that, that's going to be 12. We know that f prime prime of 1/2 is a different one in my problems, so we'll do it this way. Okay, f prime prime of 1/2 is going to be 12 times 3 times 1/2 is 3/2 minus 1 is 1/2 times -1/2. That gives us 12/4, which is -3, and f double prime of 2. I had pre-calculated that. I won't bore you with the calculation, but that's 60. So let's see. Just wanted to answer a question. So if prime prime is increasing. Okay, sorry, I was just looking at the chat, and yes, those answers were correct. So f prime is for increasing, decreasing, and f double prime is for concavity. Oh, Eric is asking, what was the purpose of using the second derivative in the first part? The answer is that we're just trying to figure out whether 0 or 1 are mins and maxes, because we know that if it's a max, then it looks like this, which gives us what's going on the right and left of the critical number, because we know that if it's a max, it has to be increasing to the left and decreasing to the right. So it's just kind of a shortcut to finding what's going on to the left and right of that point, and also being able to draw the point as this shape. I think you'll see it when I get down to the when I actually draw the graph. Where are we getting 1/2 from? I just picked it. It's a number that's in between 1/3 and 1/2 and 1. You just want to pick an arbitrary number that's in between the transition points. So why are both sides positive? Oh, both sides of, you mean over here. Why are both of these positive? It just comes out that way. I've got 12 times a positive number times the square of a negative number. So that comes out to a positive number. Wouldn't that mean it's not a transition? No, it doesn't mean it's not a transition point. It just means that a transition point is sort of a candidate point for when we might see a change in the shape of the graph. It turns out that actually we do see a change. That even though, which one? Sorry, which one was it? At x equals 1, what we saw is that the monotonicity of the function is not changing. It goes from increasing because the first derivative is positive on one side and positive on the other. So it is actually increasing on both sides. But what we're going to see here, as we're going to see with the green calculation that I did, is it's increasing. This is going to be x equals 1, and then it's still increasing, but it's changing its shape like that. So because it's not transitioning from increasing to decreasing, but it is transitioning from concave down to concave up. So if you notice here, let me just go back to this part. I have positive concavity, negative concavity, and positive concavity. Correct. I did the second, yeah, the question was, you did the second derivative test to find local extrema. Yes, that's correct. Because local extrema are part of the shape of the graph. Why use the second derivative instead of the first? You actually could use the first. You could have simply looked for whether the first derivative is positive or negative to the left side of the of each transition, to the left and right side of each transition point. There's no particular reason not to do it other than the second derivative test is usually easier to apply if it works, because you only have to calculate one number in order to use it. And once you found it, that already automatically tells you whether the first derivative was negative or positive on either side of the transition point. Why is x equals 0 a local min? So what did we find here? We found that f prime prime of 0 is equal to 12. So that means that the function is concave up at 0, and that makes it a local min. That means that the shape of it is like that. Makes sense? Okay. There's just one more thing that we have to do. We want to investigate the asymptotic behavior of the function, or rather its behavior as it goes out to positive infinity and negative infinity. In other words, if this is the x-axis, we want to ask what's going on there and what's going on there. So we know that the limit as x approaches infinity of the original function, which I've lost sight of already, and I'm going to graph it in a minute, and you'll see. So the original function was 3x to the fourth minus 8x cubed plus 6x squared plus 1. And the limit as x approaches infinity of that is infinity. And we also know that the limit as x approaches infinity of the same function is also equal, as x approaches negative infinity, is also equal to positive infinity. So what that tells us is that if we go off in these directions, the y values are going to look sort of like that. All right, so now let's get back to the graph and we'll see what this looks like. Okay. I'm not going to draw this totally to scale. I'm just going to put in the transition points like this, like that. And so now what we want to do is we want to say what f prime and f prime prime are, because that's going to give us the shape of the graph. So what we determined actually is, first of all, we determined that there's a local min here. So I'm going to put in dotted lines at all the transition points so we can mark whether the first and second derivative are positive or negative on the left side. So since this is a min, what we know is that f prime is negative on this side and positive on the right side. That's what I meant when I said the second derivative test automatically tells you what's going on to the left or right of a critical number, is by finding out that this point is a min, that automatically tells me that it has to be decreasing to the left and increasing to the right, because that's what a min is. What we then found was, see, we found when we performed the first derivative test on the critical number 1, we discovered that it was increasing on both sides, positive first derivative on both sides of that number. So I'm going to put in positive here. The transition points for a concavity were actually at 1/3 and 1. And what we saw, I believe, is that function was concave up on this side of 1/3. That's from the other page. I don't want to flip back to it now. There was no transition in the second derivative at 0, so nothing changed across 0 about the second derivative, and it's still positive there. We saw that the second derivative was negative in this region, and we saw that it was positive in this region. We also know that given that this is the function, we can easily put in that f of 0 is equal to 1. So that's actually a point on the function, and it's a local min like this. So I know that it's going to look sort of like that. Let me make this a little shallower. The local min, and it's concave up like this. And I know that it remains increasing, but switches from concave up to concave down at this point here. Still increasing though. Notice that as I point to this, the first derivative shows that it's still increasing. So even though it's concave down, the function is increasing, and then it switches back here to increasing and concave up. So I've got concave up like that, concave down, concave up here, and this is a min. This is an inflection point. This is also an inflection point. And we also investigated the asymptotic behavior. Recall that was the last thing that we did. Said that it's going to have to go out to infinity as x approaches positive and negative infinity. So I can draw that in, and already drawn it in on the right. And there you go. That's the graph of this function done based on its derivatives. How do we know it's positive infinity on both sides? First of all, sorry, I'm going to get back to Troy's question in a minute. As to Daniel's question, how do we know it's positive infinity on both sides? If you take the limit as x approaches infinity of that function, we had a rule in the other, back in chapter 2, as to depending on whether the highest power is even or odd, as to whether the function will approach positive or negative infinity. So a function that has a highest power that's even is going to approach positive infinity on both sides. Function that has a highest power that's odd with a positive leading coefficient is going to approach positive infinity on the right and negative infinity on the left. So as to Troy's question, we can always use a graphing calculator to graph too. No, that actually kind of sidesteps the whole point. The whole point of the exercise is to be able to figure it out from its derivatives. In fact, when you get to the workshop tomorrow, I have an exercise where I've basically just given you, rather than give you the actual function that you could put into Desmos or a graphing calculator, I just tell you what the function is doing: concave up, concave down, increasing, decreasing on certain intervals where its asymptotes are, and ask you to draw the function. So you should still be able to do it based on these principles. Okay. Anyway, that's it. I apologize that I didn't record the first couple of examples. Sometime this afternoon, I'll go back and re-record those. Unfortunately, you won't be able to get the questions, but I will have a recording of the first couple of examples in case anybody wants to see it. So have a good rest of the week, everybody. You're free to go. I can stick around for a couple of minutes, and then I'll start office hours at 12. Eric's going to ask a question. I do not know who Carol Baskin is. Maybe I should.